Hey y'all, it's Professor McDonald. In this video, I'm going to explain how to answer this question where the directions ask us to complete the square to rewrite the given polynomial in the form x plus a quantity squared plus b. Now, first thing I'm going to do is write down an example, x squared minus 6x plus 7, and we're going to rewrite it in this form, x plus a quantity squared plus b. And I'm going to explain how to answer what a equals and what b equals in the end. So we're shooting for, or here our goal is to figure out what that a should be and what that b is. Okay, so I'll teach you how to answer this question. But then as a bonus, I'm going to explain why it works, completing the square that is, and I'm also going to explain when you might use this or how knowing how to complete the square is extremely useful. So let's begin with just answering the question. We have started off with a polynomial that is quadratic, meaning the highest power of x is 2. And if you were to graph this, it would be a parabola, a horseshoe shape. Now, it's not a perfect square right now, and a perfect square is one that if you take a binomial, let's just use a random example like x plus 3, and quantity square that, and you multiply it out, you'll get a perfect square trinomial result. All right, and we'll talk about a little bit more about that in a moment. So what we're trying to do is force this polynomial to be a perfect square polynomial, at least part of it, and then we're going to have an extra number added on the end. So what we want is a perfect square trinomial that we can rewrite as a binomial squared, and then another number added on. So what we're going to do is we're going to move the positive 7 out of the way, because if that were a perfect square trinomial, then both the first term and the last term would have to be perfect squares. And they're not. 7 is not a perfect square. X squared is, because the square root of x squared is just x. But if you take the square root of 7, you get an irrational number. So that doesn't work out. We want to make it perfect. So now what I'm going to do is I'm going to add something that's going to make this portion into a perfect square. Something that I can rewrite as x plus or minus something, quantity squared. And then I'm going to have some extra number added on the end. Well, if I'm going to add something to this original polynomial, then certainly I would have to also subtract that exact same amount. Otherwise, I would be changing the value of the overall statement. So now I'm going to put in something that's going to complete the square for me here. Now, what I need is half of the middle term's coefficient. So that would be negative 6 divided by 2 would be negative 3. And then I also want that squared. So I'm just going to rewrite that with parentheses. So I want negative 3, half of the middle term's coefficient, and quantity squared. Well, negative 3 squared is negative 3 times negative 3, which would give you positive 9. So I've just added a 9, which means I need to also subtract a 9. So now I can take this portion, these three terms, this perfect square trinomial, and rewrite it in the form of a binomial squared. So I'm going to have now x is the square root of this term, right? need to undo that. The square root of this term is just x, and the square root of this term is going to be -3. So now I've got my perfect square trinomial rewritten as a binomial squared. Now, the leftover part here is +7 minus 9, so that gives me -2. So I figured out that the a is -3, right? Because it says plus a, so plus a -3, and the b is -2. Now, I've shown you how to answer the question, but now I want to talk to you as a bonus about why this makes sense. I kind of showed it to you before. A perfect square trinomial, an example of a perfect square trinomial is the one we just completed ourselves. We made x squared minus 6x plus 9. So how can you look at a polynomial, a quadratic polynomial, and tell if it's a perfect square? Because the square root of the first term is a nice rational number, and the square root of the last term also, right? And so what about the middle term though? The middle term, if you were to take the x and the 3, you'd get 3x. Now, if that's a -3, which it should be because you have a negative here, then you would have -3x. Now, if you double that, what do you get? Double this and you get -6x. So the pattern you're looking for is a perfect square with x in it on the front, some other perfect square on the back, and in the center, whatever the product is of the square roots, you would double that. And that would give you a perfect square trinomial. And if you can recognize that pattern on a perfect square trinomial, then you can easily, quickly factor it, and factoring is very useful, and we'll talk about why in a moment. But you can just rewrite that as x minus 3 quantity squared. Okay, so that's important to note. So it works the other way around. If I start with x minus 3 quantity squared and multiply it out, any perfect square binomial is going to have the same basic thing happen. You're going to FOIL it out, so you're going to do x squared. That gives you the first in FOIL, so I'm just using distribution here. Then -3x, that gives me the O in FOIL for my outer terms. The inner terms give me -3x, so that's the I in FOIL. And then the last two terms give me +9. And then what always happens in the center there is a duplicate term that when combined gives you twice the amount of one of them, right? So that's the whole pattern of perfect squares and perfect square trinomials. You can have a perfect square trinomial that will factor to a binomial squared. Or the other way around, you can have a binomial squared that multiplies out to become a perfect square trinomial. And this is useful. Let's talk about one of the uses for this. Let's say we were asked to graph that same quadratic polynomial as a function. So f of x, remember, can also be thought of as the y value or the vertical locations. So we're going to graph this. What you would want to do is first recognize that it's quadratic. So in your mind, you immediately start thinking, oh, it's probably like this or possibly like this, right? It's a parabola. If the lead coefficient is positive, then it's a happy parabola. If it's negative, then it's a sad parabola. Okay, so far looking at this, if I know anything about quadratic polynomials, quadratic functions, I would know that it's going to be a happy shape like you see here. The next thing I would want to know is where is the vertex, the lowest point of my happy parabola? Well, if I complete the square like we did previously, then I would have x. Oh, I think I have a typo here. This should be a -6. So I'm trying to do the one that we were just working on. So just to show you what I was really trying to do, I was trying to show you this original polynomial, x squared minus 6x plus 7, and how it can be graphed from the form we put it into, which is x minus 3 quantity squared minus 2. So we changed it to that form. So when we come in here with x minus 3 quantity squared and minus 2 added on the end, this is what we can call vertex form. It's typically known as vertex form because when a quadratic function is written in this form, you can quickly identify the vertex. And we typically refer to the vertex with symbols. Now it's a point, right? It's a point with an x and a y coordinate, but we often call them h and k because they're special. That way everybody knows we're talking about the vertex. All right, so h and k are the coordinates of the vertex. So I'm going to rewrite this as h and k. So how would I know that it's 3 and -2? You might have noticed already that the 3, a positive 3, that's this part without, ignoring the negative. The 3, or the opposite of -3 is positive 3. That's my h. And the -2 is exactly what we see right here. Okay, so the vertex form, when written out in general, of a parabola or a quadratic function is x minus h quantity squared plus k. And so the built-in negative here in front of the h tells you that you always use the opposite sign of what you see in your vertex form. And the positive in front of the k tells you that you don't change the sign. So I'm able to quickly look at my vertex form of my parabola after completing the square and see that my vertex is going to be at 3, -2. That's going to be my vertex. I can see it very quickly. So it's definitely useful for that reason. Another reason it's useful is when you're graphing a parabola, we went through 2 steps. We realized it was a quadratic, so it was a horseshoe shape, a parabola shape. We noticed that the lead coefficient was positive, so we knew it would be a happy parabola. And then we found the vertex, which is a very key point to graphing a parabola. But parabolas can be very narrow or very wide, right? And so there's all different ways this parabola could turn out to be. So we don't have enough information just by finding the vertex. Based on the position of our vertex, though, we know that our parabola is going to go through the x-axis. And on the x-axis, the y value is always equal to 0. So this is convenient because now I can replace the y value or the function value with 0 and then solve for x. And what this is going to do is it's going to help me find my x-intercepts, right? Because whatever this point is, you can see the y value is 0 on both of these because they're sitting on the x-axis. So now that I've set the whole thing equal to 0, all I have to do is solve and get x by itself, and then I'll have my x coordinates that are going to go to tell me where to place, my x-intercept so I can make my parabola, complete my parabola drawing. So from this form, it's super easy to do because now I can use the square root method to solve. So what am I going to do? I'm going to add the 2 to both sides. So then I'm going to have 2 equals quantity x minus 3 quantity squared. And then what do I do from there? Well, I want to get rid of the square, so I'm going to take the square root of both sides. And remember that I have to put a plus minus here. And then what I'm going to have from there, let's move this down a bit so I have a little more space. Oh, no, that was messy. Let me pause and reposition everything nicely for us. All right, so now let me simplify what I had done in the last step. So now I have the x minus 3 is equal to plus and minus the square root of 2, right? So to get x alone, I just have one more step, and that is to add 3 to both sides. So now I'm going to add 3 to both sides, and so what I'm going to have is 3 plus or minus the square root of 2 is equal to x. So this means the plus and minus part of this means that I have two values for x. X can be 3 plus the square root of 2, and x can be 3 minus the square root of 2. And if you calculate these, for each of these, you're going to get 3 plus the square root of 2 is approximately 4.414. So that's what you see here. And 3 minus the square root of 2 is approximately 1.586. So that helps us know exactly where to place our intercepts and how to finish graphing our parabola. So that's just two reasons that I love using completing the square. Just to kind of summarize that, first of all, it makes it much easier for me to locate my vertex. And then second of all, much easier to find my x-intercepts if I want to graph a parabola. And completing the square is also useful when you're trying to find the center of a circle. And it's useful for solving quadratics in general. So if you ever see a question like solve x squared minus 6x plus 7 equals 0, that means to find the value of x that would make this statement true, or values. And if you notice, that's what we just did to find our x-intercepts, right? So anytime you're being asked to solve a quadratic, you're, in a sense, being asked to find x-intercepts. And there's three different ways you can solve a quadratic. You could factor it if it's factorable, which this one is not. And then when you factor a quadratic, you can set each of the resulting factors equal to 0 and solve for x. If that's not possible, then you could use the quadratic formula, which many people have memorized and like to use because it works every time. That's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so you could use that. Or you could complete the square in order to use, I guess I should say it this way, you could use the square root method. Now the problem with the square root method is that if it's not already a perfect square, you have the added step of completing the square. And many students don't like to do this because they feel uncomfortable with it at first. But once you realize how easy it is, or once you get used to the pattern, it makes it possible to solve any quadratic. Just like the quadratic formula works every time, and that's why we like the quadratic formula, okay? This also works every time, as long as you know how to complete the square, if you use both of these together, okay? So just to give you one more example, I'm going to show you how solving this with the quadratic formula would have worked. and then show you again how fast we were able to do it using the third method here. All right, so with that same parabola or that same quadratic polynomial, let's solve using the quadratic formula first. So I'm going to do, remember the formula is x equals negative b plus or minus the square root of b squared minus 4ac all over, well, not the x part, all over 2a. And that is only when your quadratic polynomial is in this format where it's all set equal to 0 and the terms are in order by their powers of x. And then you have your a is the coefficient of x, your b is the coefficient, I meant to say a is the coefficient of your x squared, b is the coefficient of your x, and c is the constant term. Okay, so here we have that a is equal to 1, b is equal to negative 6, and c is equal to positive 7. So then we go and we start plugging these in. So we have negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And then you simplify. So negative 6 is positive 6. Negative 6 squared is 36. Negative 4 times 1 is negative 4. Negative 4 times positive 7 is negative 28. And then you get 6 plus or minus the square root of 8 all over 2. And now you have to either do this in the calculator to get your decimal approximations, or you can simplify a little further by simplifying the radical, because this is the same thing as 4 times 2. So the square root of 4 is 2, right? So I'm simplifying from here to here. And then I have this 2 that divides evenly into both the 6 and the 2. So we can simplify this to 3 plus or minus the square root of 2. And if you recall, that is what we got when we used the square root method. Okay, we got 3 plus or minus the square root of 2 right here. And to me, it's way easier to do the completing the square and then use the square root method. Because you get, by completing the square, not only do you identify the vertex, but you find both of your x-intercepts pretty quickly. So I prefer completing the square because let's review how quickly that went. Completing the square with the same polynomial went like this. If I had it set equal to 0, then I could rewrite it, make some room by moving the 7 over a little bit. And then I'm going to add half of the middle term. So half of negative 6 is negative 3. And I'm going to square that. And that's essentially positive 9. So I'm also going to subtract 9 to keep it balanced. Then I'm going to rewrite this as the binomial squared and combine like terms here. And now I know that my vertex is the opposite sign for x, so it's 3 for the x coordinate, and the same sign for the k, so negative 2 for the y coordinate. And now I can go straight from there to find my x-intercepts because I add 2 to both sides, so I get x minus 3 quantity squared equals 2. Take the square root of both sides to cancel out this 2 here. Make sure not to forget the plus minus. Then I have x minus 3 equals plus or minus 2. Add the 3 to both sides. Okay, so now, sorry, that should be square root 2. So now, in just, I guess it was like a minute or so, maybe 2 minutes, I very quickly was able to find the vertex and both of my x-intercepts. That's so much better. And it just takes a little getting used to. So I hope I've convinced you and that you enjoyed this lesson, and I'll see you in the next one.